Welcome back, everybody. In this next set of videos, we're going to look at something called the dot product. And this is a special kind of multiplication that we use with vectors. So let's say we have two vectors, vector v and w, and we use similar notation that we're used to. Well, the dot product is defined as follows. So what we do is we multiply the numbers that are with the I together and the numbers with vector j together. And the result is actually a real number answer. It's not a vector. So it's a little bit different than when we did scalar multiplication, where we had a vector answer. Here we typically, here we always have a real number answer. There are some properties as well that we can keep in mind. So one is you have the commutative property here, so it doesn't matter the order in which you start it, which makes sense because when you're multiplying two numbers together, the order doesn't matter there either. So you have that commutative property. You also have the distributive property here. So you can either add two vectors first and then apply the dot product, or you actually can distribute and apply the dot product to each one and then add and get the same answer. Using a scalar, I guess not scalar, using a dot product with 0 would result in an answer of 0. And to be clear, this is vector 0. If you use a dot product with the same vector on itself, you can do it out. You can do it the multiplication, but you end up getting the magnitude squared. And then another property that is helpful is if you're trying to do a dot product as well as scalar multiplication, you can actually take that scalar factor out, do the dot product of the vectors, and then multiply, or you could do it the other way. You could bring the scalar in with the other vector, do that first, and then use the dot product. So again, a lot of regrouping allowed there when you have the dot product as well as scalar multiplication at the same time. So here are two vectors that we're going to use, and we're just going to do a little practice with the dot product. So again, you want to remember that the formula there is to just take the A values and multiply them, take the B values, and multiply and add them together. So for V and W, my A values are 5 and -3, and my B values are -2 and 4. So I have -15 minus 8 there, and we're looking at -23. Now for the next one, I'm doing the dot product with itself. So again, you can either do it out if you want to, or we can use that shortcut. I'll show you how both work. If I want to just do it out, I would take the A part, so the I part, and multiply it with itself. And then I would take the B part and multiply it with itself. So you have 25 plus 4, which is 29. If you want to use this little shortcut formula, well, first of all, the magnitude of V is the square root of A squared plus B squared. So A is 5, B is -2. So you have the square root of 25 plus 4, which is the square root of 29. And then when you square that, you do get that same value of 29 there. Sorry, let me move that up so you guys can see it. So I did it out the regular way, or I used that shortcut from number 4, and they both gave me the same answer. So again, it's a nice kind of quick, easy computation, and your answer should always be a real number result. So keep that in mind. You're not getting a vector output here. You're getting a real number output. Now there is an alternative formula for the dot product, and I have it written out here for you. Again, if you need to pause the video at any time, go ahead and do that so you can take the notes down, or make your own extra notes as well. So this is an alternative formula. It still gives you the same dot product answer, but it uses the cosine angle instead. So what you do is you take the magnitude of each of the vectors and multiply them, and then you also multiply by the cosine of theta. And theta is the smallest non-negative angle between the two vectors. Now, how do you find theta? We do have a formula for that here. So again, this is not helpful in every case. This would be helpful if you're already dealing with angles and things to begin with. But to find that angle, we basically have this idea. So we're going to use the inverse cosine. And what you do is you take the dot product of the two vectors on top, and then you divide it by the magnitudes. Again, This formula tends to be most helpful if the theta is easy to find. Otherwise, you can sort of just do out the work there, but we can still use this other alternative formula. So let's go ahead and try it. So let's find the angle between these two vectors, which is 3i minus 2j and negative I plus 4j. We're going to round to the nearest tenth of a degree here. So here I'm just finding the angle. So I'm going to go ahead and use this formula. So the first thing I'm going to do is I'm going to go ahead and I'm going to find this piece here. So I'm going to do the dot product first. So here I'm going to multiply my two a pieces together. So what's with the I. So I have 3 and negative 1. And I'm going to go ahead and add it with the second part. So the negative 2 and the 4. So I have negative 3 minus 8, which is negative 11. And then in the bottom, I do have a little bit of work, so I'm going to just take my time for a second. I'm going to go ahead and find the magnitude of v first. So it's going to be the square root of 3 squared plus negative 2 squared. Well, 3 squared is 9 and negative 2 squared is 4. So square root of 13. And then I'm going to go ahead and find the other magnitude. So I have negative 1 squared plus 4 squared. So that's going to be 1 plus 16, which is 17. And then when I multiply those together, I'm looking at the square root of 221. So just using my calculator for 13 times 17. So what I get for this formula is I get negative 11 over the square root of 221. Now I'm going to go ahead and find the angle. So the theta that I'm looking for is going to be the inverse cosine of negative 11 over square root of 221. And when you use your calculator there, again, make sure you're in degree mode here because that's what it asks for. You get about 137.7 degrees. We can also talk about if vectors are parallel or orthogonal. And it's a similar idea to what we've done with lines with parallel and perpendicular. So parallel vectors are vectors that have an angle either between 0 or 180 between them. So for instance, if we have vectors that are going in the same direction, and again, they're lying along really the same line, the angle will be 0 there. So those are parallel vectors, they're going the same direction. Here, the angle between the two vectors is 180 degrees, right? If I look at this flat line, it's 180 degrees. So they're going in opposite directions. So there's different ways that angle or vectors can be parallel. They can either be going the same direction, in which case the angle between them is 0 degrees, or they could be going the exact opposite direction. They still form this sort of like straight line though, so their angle between them is 180 degrees. Instead of saying perpendicular, we use the word orthogonal, and two vectors with the angle of 90 degrees between them are orthogonal. So for instance, maybe one vector goes this way and the other vector goes that way, and you have a 90 angle between them. We can also check officially if two vectors are orthogonal by using a dot product. So it's always good to look, that's a great starting place, but remember we do really need to check algebraically and computation that these things are true. So two non-zero vectors are orthogonal if and only if their dot product is 0. So that's a great way to check if you do have this sort of perpendicular idea here with your vectors. A little note here, the 0 vector is always orthogonal with any other vector because the 0 vector will produce a 0 dot product. So for an example here are the vectors v equals 6i plus negative 3j and w equals I plus 2j orthogonal. Now you could graph them as a way to start, but it's better to actually check them algebraically or computationally here. So I'm actually going to go ahead and find that dot product. So remember, for the dot product, we multiply the A values together. So whatever's with the I's. So 6, and then here would be a 1. And then we multiply the B values. So -3 and 2. And we add them together. We get 6 plus -6, which is in fact 0. So yes, these actually would be orthogonal. If we were to graph them, we can see that that they do have that nice 90-degree angle between them.